Okay, so let me remind you where we are. We last time looked at the Ford-Fulkerson algorithm, and we finished describing it. We proved that if the capacities are all integers, then the algorithm definitely terminates. We don't know what happens if the capacities are irrational. I mean, we know. I mean, I know, but you haven't seen a demonstration that it doesn't terminate. But in fact, one can cook up examples like that. And then I suggested that a nice homework question was what happens if the capacities are rational, not irrational. And the book discusses that, so that one's gone. So what does happen if the capacities are rational?
You just multiply by the largest, by the, I guess, the least common multiple of the denominators, and then you end up with integers, and you're back to where you started.
Yeah, I mean, if you can just take some value that you multiply all the capacities by, and it turns everything to be integers. So what you would multiply by is the least common multiple, I guess is what it's called, of the denominators. And so everything becomes integral. Then we know at least that we would have finite integers then, and then we could run the Ford-Fulkerson algorithm and then scale everything back by that same amount, by dividing it. Now the time for that algorithm then would of course increase. I mean, it's the time we saw last time was related to the total capacity or the total, the largest capacity. That was the time bound that we put in there. Now we can put a better time bound with this, but nonetheless, if the total flow is c, then the time for the Ford-Fulkerson algorithm is the number of edges times c. And when you multiply by something, you make c bigger. But anyway, at least we have finite termination. We have termination if it's integral. And that's something that we don't have and rational. But that's something that's not true if it's irrational. Okay, so where we ended last time was in the statement of the max flow min cut theorem, and that the value of the max flow is equal to the capacity of the minimum cut. And we had also seen earlier that the value of, if f is any flow, then, and AB is any ST cut, or this is an ST flow, then the value of that flow is less than or equal to the capacity of that cut. For any, I should emphasize ST flow, but whenever I say a flow, it means particularly, it's from the source to the sink, and that's actually, or to the terminal. And that's actually part of what we define to be a flow anyway. But I'm putting it there for emphasis. So we always have this relationship. And we also showed, in fact, that's how we got to here, was that you can measure a flow across any cut. Okay, so if here's S and here's T, and this happens to be any ST cut, then you can measure the flow by taking the amount that goes in that direction minus the amount that goes in that direction. And that's always going to be the value of the flow. And in fact, that's then implies this, right? Okay, and then this implied the following conclusion. If F is a flow and AB is a cut, where the value of that flow is equal to the capacity of that cut, then VF is max. It's the maximum possible flow value, and CAB is the minimum cut capacity. And, well, okay, we already said they're equal. Okay? So all we have to do to prove this theorem is what? We have this already. This is our conclusion from last time. We want to go to this theorem which says that there's always this equality of the max flow and the minimum cut capacity. So how do we get there? Well, this thing says if F is some flow and AB is some cut, it has this relationship, then we have this conclusion, but that's what we wanted, right? Okay, so this implies the theorem, max flow min cut theorem. Okay, so what's the answer to my question? How do we go from this to that? Yeah, we just have to exhibit. We have to, but in a general way, in an abstract way that says that for any network, we can always find such a flow and such a cut that has this relationship, and therefore that implies this theorem. Okay? So that's the game plan. All right. And so here is the flow and the cut that we'll use. F is the flow at the end of the Ford-Fulkerson algorithm. Well, we were trying to prove that the algorithm is correct, that it actually proves that it actually finds the maximum flow. So that doesn't seem too surprising that we're going to use that one. And actually, let me put a star there. I don't know why. So that's the flow at the end of the algorithm. Okay. The cut that we'll use is a little more subtle. Let GF star be the residual graph for this ending flow. So you remember in the algorithm has a flow. It starts from a flow of 0, and it's always building this residual graph. And then it's trying to find an ST path in that residual graph. And if it finds one, then it changes the flow. And it keeps doing that until it can't find an ST path. That was the termination condition for the algorithm. At that moment, F star is the flow that we have in our hands, and this is our residual graph. Okay, so here's S again. And, well, now this time this cloud is the residual graph, but let's not. Okay, so from S, and this is in GF star. This is the residual graph, and it has, I'm just drawing, a picture here. Okay, so this is going to be the set of nodes. A equals the set of nodes reachable from S in GF star. Okay? Well, obviously S is in A. Okay, is T in A? No, because if T was reachable from S in the residual graph, then there would be a path from S to T in the residual graph. But the termination condition is precisely that there is no path from S to T. And so so in particular, T is not contained in A. Okay. And we let B equal the entire vertex set minus A. All right, and so we know that T is contained in B. So we have a ST cut in our hands here. The algorithm finishes. When the algorithm finishes, we can extract from the residual graph this particular ST cut. And in fact, to emphasize that it comes from this flow, let me I think the book has stars in here, so let me try to follow that as much as possible. Okay? So A star, B star is an ST cut. Okay, so we have our flow, our candidate flow, we have our candidate ST cut, and I want to prove that they have this relationship. Okay. I want to show that VF star is equal to C A star B star. Okay, so now is the point where we draw the clouds. Okay, here's S, here's A star, T is over here, and this is B star. Okay? And this is in GF. This is a cartoon of what the residual graph looks like at this moment. Okay? So in this residual graph, let's look at an original edge that goes from A to B. So this is, E is contained in G. It's an original edge which goes from A to B. What can we say about it? What do you know about that edge at this moment? Or the flow in that edge at this moment? It's what?
It's at maximum.
It's at maximum capacity, right. Okay. F star, so I'll put it this way, for if E is an original edge going from A star to B star, the flow in that at this moment must equal its capacity. Because otherwise, there would be a forward edge, this particular forward edge, or with some capacity number on it, would be in the residual graph. And therefore, this wouldn't have been the set of nodes. Well, it's implied at all. I'll put that word in there for emphasis. If there was this edge here, then A star wouldn't have contained all of the nodes that were reachable from S. Okay? So we know that we have this relationship. Now, what about for put a little for emphasis there, that was from U to V, but suppose we have an original edge that goes from V to U. VU, if the original edge in G goes from B star to A star, okay, then what can we say about what can we say here? Okay, remember this picture, this cloud here, which contains S but does not contain T, that's in the residual graph. But now I'm talking about original edges that were in the original graph. Okay, so in the original graph in G, there's an edge that goes from B star to A star. And what's its flow at this moment, the moment that we're talking about? What's its flow in F star? It's what? It doesn't have any. Yeah, okay, so its flow is 0. Because if it did have any flow, if there was a flow here, then there would be a back edge like that in the residual graph. And therefore, again, A star wouldn't contain all of the nodes that were reachable from S. So we'd again have that same contradiction. So we know that any edge original edge, which goes from A star to B star, its flow must be at its capacity, and any edge that goes from B star to A star must have flow 0 at this moment. Okay? So what do we know about so VF is equal to, well, I think we have better notation. it's the flow out of A star, is the notation we had last time. It's, well, actually, this is always true. We proved that in general because A star, B star is a cut. So we have that, but now what is this? This is 0, right? That's what we were just saying. The flow into A star on any edge is 0, so that one goes away. And then what's the flow out of A star? That's equal to the summation of E, CE, E out of A star. And that, by definition, is the capacity of A star, B star. And so we've proven what we intended to do. We have a flow. Oh, I should have put this as a star. We have a flow, which is the last flow we have in our hands from the algorithm. And we have an ST cut, which also comes constructively from the algorithm. And the relationship between the value of that flow and the capacity of that cut is an equality. This step is perfectly general. This has to do with any ST cut. Okay? But then we argued here that this amount is 0. And we argued here that this amount is equal to every edge that's going out of A star must be, its flow value must be at its capacity, and that gives us this part. But the definition of the capacity of A star, B star is precisely the summation of the capacities out. Remember, we don't subtract off the amount in. Okay? So that's it. We've proven there is such an F, there is such an A star, B star. We get the equality, and we've proven the theorem, which is the max flow min cut theorem. It's not just a theorem. It's constructive. Well, it is a theorem, but anyway, it shows you constructively how you can find the max flow, and constructively how you can find one min cut. Okay, so however, if you think about the logic all the way through, from the very beginning, we really have only proven this for integers or for rationals, because this proof relies on the existence of an algorithm that terminates. And we've only proven termination for rational capacities. Okay? But in fact, it turns out that this theorem is true for even irrationals, even though the Ford-Fulkerson algorithm doesn't terminate necessarily with irrationals. So, and the thing to keep in mind is that if we do have such a flow and such an ST cut, no matter how we got it, whether we got it from the algorithm or not, it'll prove this. So when we look at the next algorithm, we will see that we have this ending relationship in that algorithm as well, and therefore we'll have this conclusion. And that algorithm will not depend on the capacities being rational. So at that point, we'll have proven this theorem for all possible networks. And this is one of the really classic, nice combinatorial theorems connected with a constructive algorithm. And this relationship, the max-min relationship, comes up in very, very frequently in a lot of different applications. And as I mentioned last time, this itself is a specialization or special case of what's called duality theory in linear programming, which is also a max-min relation. We won't cover that in this class, but if you ever see linear programming in the future, maybe some of you already have, then you'll run into that max-min theorem and be able to connect it to this material. Okay, so one more corollary that comes from the algorithm. Another corollary that's very useful. If all the capacities are integral, then all FE values will be integral by the Ford-Fulkerson algorithm. Let me parse this a little bit better. I really put this poorly. If all the capacities are integral, then if you just look at the action of the Ford-Fulkerson algorithm, the flows that are assigned are always integral. Okay, initially there's an S to T path, and we find the minimum capacity along that, and that's the initial amount that's put on each of those edges. And since we started out with integers, that's integral. What you're doing after that point is adding or subtracting the minimum in a path in the residual graph, and that minimum will also always be an integer value. So you're ending up with integer values at every step of the algorithm. So the Ford-Fulkerson algorithm ends up with integer values that are assigned to all the edges, and so that shows that that there always exists an integer assignment. Will be integral. Well, maybe I should just say this at the end. The end. Put it that way. Of the Ford-Fulkerson algorithm. That doesn't mean that all flows. It doesn't mean that all flows will be integral. You can find other flows that might not be integral. Okay, and that's why originally, the way I originally wrote this up was a little bit misleading, because it sort of suggested that all maximum flows are going to be integral if you start with integer capacities. This just says that you can always end up with integer capacities if that's what you want, because the Ford-Fulkerson algorithm will give that to you. So that's a constructive proof of that there always exists in integer flows, and that's a very useful thing. Okay, so let me show you now an application, one of the standard applications of the algorithm, and I'm not sure we'll see an application of the maximum min-cut theorem. And then after we do that, I'll go on to start talking about the other algorithm, max flow algorithm, which is going to be faster than the Ford-Fulkerson algorithm. So this is bipartite matching. So actually, we've seen matching, stable matching problems, and we've seen the word matching, I think, in the alignment. But at any rate, this is a different kind. So a bipartite graph is, first of all, one that has two sets of nodes. And just draw one here. So this is set A, for example. This is set B. And the only edges that a bipartite graph can have to run from A to B. It doesn't mean that every possible edge is there, but there are no edges between two nodes that are in A, and no edges between two nodes that are in B. Okay, so here is just an arbitrary example. Okay, so a bipartite graph has two sets of nodes, A, B, and any edge connects a node in A to a node in B, like this. Okay. Now, matching is some subset of edges such that no two edges touch. So matchings turn out to be useful in a lot of different applications, what you're looking for is often a matching in many applications. So a matching is a subset of edges where no two edges in the matching, let's call it M, touch. So actually, if you remember the definitions that were given for in the stable matching section, the first 10 or so pages of the book, I think they literally define a matching, and they also, before they define a stable matching, and they also define a perfect matching, which is one where it's a matching where every node is touched. Well, of course, that would mean that you have to have the same number of nodes in A as in B. So if you have a different number of nodes, you can't have a perfect matching. Okay, so everybody clear on what a matching is? So it could be some of the applications of matching. Why do you want to find a matching? Maybe, well, even let's say in the stable matching context, maybe each edge here just represents the fact that this person is willing to marry that one. And whereas in the original stable marriage problem or matching problem that we looked at, every individual had a full list, preference list of all the others, or every male for every female for every male. But now let's say that some are just not acceptable. And so this person, maybe this is the men, these are the women, this man only finds these two women acceptable. And now we're not looking for a stable marriage or stable matching anymore. We're just looking for a matching given these particular preferences and or constraints. And what we want is the largest possible matching. So we want the maximum cardinality matching. Okay. So if we just look at this example, I don't know, I'll just guess here. Maybe take that, and then this seems like a good thing to take because this one has some other options, and we can do that, and we can do that. Okay, it's a very messy picture, but we ended up matching all of the nodes in B, so that must be the largest one because even though there's a node in A that's not matched, that must be the maximum cardinality because everybody in A is matched, and you certainly can't do more than that. And you'll see this edge is, well, there's an ambiguity in the English language, right? Matching, they don't touch. Okay, well, do these two edges touch? They do. But I mean touch at a node, okay? Yeah. And since we did problems where the issue was crossing edges, I shouldn't mix these kinds of terminology. I should be very clear. What I'm talking about here is touching at a node, because you really want to match this individual in the context of the marriage or stable matching kind of thing. You want to assign this individual to just one other individual and so on. And that's what it means for two edges not to touch. Yeah?
So in this example, you have one node in A that's not connected at all.
One node in A that's not connected? Well, it's not part of the matching.
It's not part of the matching.
It's connected in the graph. And it can't be part of the, well, we may have another maximum cardinality matching where this is matched. It's used, but then something else in A must be not unused because there are only 4 nodes down here, but there are 5 there. So some node here is going to remain unmatched. It's possible we can find another matching here of size 4 where this one is used. Okay. So in fact, let's just think about that for a moment. If we do force this one in, so we definitely want to use that one, okay, then we'll have to not use this edge, right? And so we can erase that. And then you'll see at that moment, we have a matching of size 4 again, but now it's this node that's not used. And we had here what's called an alternating path. And in fact, you can always move from one matching to another matching via an alternating path or an alternating cycle. That's a classic kind of result. All right, so this is what we want. We want the maximum cardinality matching. Now, what kind of an algorithm do we have to find it? Anybody suggest an algorithm for that? The maximum flow from where to where? Okay, so we're going to create some additional nodes. Which ones?
One connected to the A's and the other one connects to the B's, and then try to do the flows.
Okay, and then in setting up any network flow problem, we need to know the capacities on the edges. What should those be?
Equal units for each of them.
Okay, so
To end up with matching.
an equal, but which equal to what particularly?
1.
1. That should, yeah. Okay, so that's fine. So I can still leave this up here. Let me erase the definition of bipartite. Everybody should know that. So here's a T, here's an S, and we connect every node in A to S and every node in T to B. Now, I guess there are two issues from this point. We've only looked at directed graphs up to this moment. We didn't look at network flow and undirected graphs. And that's okay. We can just direct all of these edges this way and direct all the edges that are across here. Anyway, direct everybody towards T, and that's fine. And then in setting up any network flow formulation, we always need to know what the capacities are. And we put a capacity of 1 on every one of these edges. So every edge has capacity 1. And then a max flow, well, because every edge has a capacity of 1 here, okay, then, well, in particular, this has a capacity of 1. If we find an integral flow, then if the edge has any flow at all, it's going to be 1, because if it's integer, it's either 0 or 1. So if it has a non-zero flow, it's going to be along there. And then, because again, the flow, if you use the Ford-Fulkerson algorithm, the flow will be integer, then we'll have either a flow of 1 in here or a flow of 1 in here. We certainly can't have both, because this has a capacity of 1. And we won't have a fractional amount in either, because again, in the Ford-Fulkerson algorithm, we'll end up with an integer flow, an integer value on every edge, either 0 or 1. And so we end up with a matching. Okay, so the algorithm is convert the bipartite graph to an ST flow problem. I'm not going to write the details. We've just gone through them. Find an integral flow, and that's an important point. And this will be a matching. Well, the capacity of that matching is the number of, the flow value of that flow is precisely the number of edges in the matching. Okay, this will be a matching. The number of edges in the matching will precisely be equal to the value of the flow. Will it be a maximum cardinality matching? Yeah, question?
How do you know we don't end up with those added edges instead of original edges?
How do I know that what? About
Yeah, like the algorithm doesn't choose like.
well, the algorithm is going to construct this. So that what's given to the algorithm is the bipartite graph. And then the algorithm says, what the algorithm will do is add these additional edges from S to every node in A, and then from every node in B to T. So the algorithm builds a particular instance of the network flow problem and then solves it by Ford-Fulkerson, okay, finding an S to T flow, maximum flow. And then what we were arguing is that if you find an integral flow, that will define a matching. You just look on the edges in the bipartite part. Those edges that have a flow of 1 will define a matching. And now we're talking about whether it's a maximum matching. Well, the flow is going to have a maximum value over all possible flows. Okay? And we know that the maximum, I guess it's probably better just to go backwards, just to say, suppose there was a larger matching than the one that was given by this algorithm. So that defines some subset of edges here. That's a definition of a matching. And if you think of that edge now really as having flow of equal to 1, and you put that flow along the edge that goes into that node, and you put that same flow along the edge that goes out of that node, then you'll have a flow which is equal to the size of that matching. But that would contradict the assumption that we had a maximum flow. So the maximum flow gives you the maximum cardinality matching. So max flow. And again, I haven't written down that argument, but this argument says if you have a flow, you have an integral flow, you have a matching. If you have a maximum flow, it gives you a matching. Now think about whether it's maximum by imagining that there's a larger matching, and go backwards from it to get a flow, but that flow would be bigger than the maximum flow, and therefore that would be a contradiction. Max flow implies max cardinality matching. Okay, so that gives an algorithm for maximum cardinality matching, which is, as I said, very useful. Now, it's possible to look at the, well, one other step here. Suppose I now change the capacities of the edges that are on the bipartite part from 1 to infinity. Okay? Now if we do a maximum flow by the Ford-Fulkerson algorithm, what do we have in our hands?
Then the result might not be matching.
Sorry, what?
The result might not be a matching because you have two flows. You can have two flows in edges that are adjacent.
Well, okay, so the comment here was that maybe we wouldn't have a matching, but I'm going to find the maximum flow by Ford-Fulkerson again. So again, it's going to happen that if any edge has any edge out of S has a flow in it, it will be a flow of value 1. And then again, because the flow values are integral, it's not going to split between here. It's either going to use one or the other of the edges that are out of here. So the comment is that even if you put infinite capacities in the middle, as long as you have capacities of 1 here, and even I think it would also be, if you made these infinite, that would be fine also. But even if you had infinite capacities, as long as you have capacities of 1 here, then we would still find a matching. Now, the reason I want to do that is to force the minimum cut not to cross any of the edges in the middle. So if you set up these to be infinite, then the minimum cut or the edges that cross the minimum cut, I should put it that way, the edges that cross the minimum cut will either be from among these or from among these. Okay? Because these edges, that if they were to cross the cut would then have capacity of infinity. Okay? And for some problems, for a lot of problems actually, it turns out that what you're interested in, you're not interested in the max flow so much as you're interested in the minimum cut. And this, putting infinity here, allows you to find a minimum cut that has this kind of property, which is sometimes useful as well. Well, I'm not going to finish the thought here because it will turn into a nice homework question, either on this homework or the next one. But so the point is just to remember that you have some flexibility in the modeling. You have some flexibility in setting up the graph or the network sometimes, depending on what you're trying to achieve.